Alright, welcome to our review for Practice Exam 2. Let's go ahead and get started. First off, remember we were looking at how to compare different types of variables, two qualitative, one quantitative, or two quantitative, how to organize that data in tables, and then how to find the least squares line. So we start off with a cross-tabulation table here for gender versus employment status. So we divided the people up by male and female and whether they're working full-time, part-time, or they're unemployed. We've got row totals and we've got column totals. They ask us to express the values as percentages of the grand total here. So that means that we're going to take everything and divide it by 185. Okay, so we're going to take this whole table and divide by 185. And you can round to the nearest percent if you want to. And then we want to keep our row totals and our column totals too. So this is male and female, and then we've got full-time, part-time, and unemployed. So 55, we divide that by 185. And to the nearest percent, or to the nearest two decimal places, that's 30%. 40 divided by 185 is 22. And 95 divided by 185 is 0.52. In the second column, dividing everything by 185, we get 0.12, 0.21, and 0.33. In the third column, dividing by 185, we get 0.05, 0.11, and 0.16. And in the fourth column, dividing everything by 185, you get 0.47, 0.54, and then 1.00. So 185 divided by 185 is 1, or 100%. So now your column totals here, they might not exactly add up, and your row totals might not exactly add up because of round-off error. So here these add up exactly, and these do, and these do. So you go across the rows. That one adds up exactly. That one adds. Okay, so all of these add up exactly. Oh wait, no, here 7 and 4 is 11. So notice this last column total, that actually adds up to 1.01. So, but you want to do the 1.00, 185 divided by 185. So we got a little bit of round off error here. And then looks like these guys did the same thing. 6 and 3 is 9, 10, 11. So it looks like your last row total also, we're getting a little bit of round off error. But this should always be 100%. Now, if I said divide by, express the values as percentages of the row total, then you divide this row by 87, this one by 98, this one by 185. If I said express as percentages of the column total, then you'd use the 95, the 60, and the 30. I won't use the marginal information, quote-unquote marginal language that they used in the textbook. Express as marginal totals of. But I could say, express the data in the table as a percentage of, let's see, I guess another way that I could say it is express the data in the table as a percentage of the total for each gender. Okay, so if I said the total for each gender, then I'm talking about row totals. If I said express the information in the table as a percentage of the total for employment status, then I'm saying column totals. And then let's see here, draw an appropriate multi-bar graph to show the difference between genders for each status. So we want to show the difference between the two genders for each status. So for the full-time status, we want to be able to see male and female difference. For the part-time status, we want to be able to see male and female difference. And for the unemployed, we want to be able to see male and female difference. So we're going to have 3 sets of 2 bars then in this particular multi-bar graph. So we're going to have a set of bars for full-time and a set of bars for part-time, and then a set of bars for unemployed. And then our percentages here inside the table, our low is 5% here and our high is 30%. So let's go ahead and mark off our vertical axis in increments of 10%. So I'll do 0.1, 0.2, and 0.3. And this is going to be percent. And then this is going to be status on the horizontal. And so for the full-time males, we had 30%. So we're going to have a bar for males that goes up to 30%, about like that. And then for females, it was 22%. So I'll have full-time bar for females up to 22%, about right there. For part-time, and let's go ahead and put a key down here. Let's do the males as the white bar, and let's do females as a shading. So I don't know, let's go put females as green. Okay, so there's female. Okay, then let's see. For part-time status, we had 12% male, 21% female. So part-time, we're going to go up to 12% here, and up to 21 for the female. And the female is shaded green. And then for unemployed, we had 5% male, 11% female. So on the left side, go up to about 5%. And on the right side here, go up to 11%, about right there. And let's say I want it black as my color. And then we want a shade for female. Okay, so that's the bar graph that we want. Now, if I wanted to show not the difference in genders for each status, but the difference in status for each gender, then for each gender, those words are saying gender would be your category, and then I'd have 2 groups of 3 bars. And then remember, if you're doing row totals, then your rows are the categories. So actually, if I was doing, we've got 3 sets of 2 bars. So if I was doing column totals, percent of column totals, then the columns would be my groups. So if I was doing column totals, my bar graph would look similar to this. 3 groups of 2. Okay, next up, we're given some data for retail sales of stores in millions. And so X is the number of stores and Y is the sales in millions. And the first thing I want to do is draw a scatter plot of this data. So X is 1, Y is 1, so 1, 1, so that'd be right here. X is 2, Y is 2, so 2 to the right, 2 up. I'm just using a scale of 1 on the axes here. X and Y. When X is 4, Y is 5, so 4 to the right, and then 1, 2, 3, 4, 5 up, right here. And then X is 7, Y is 9, so 1, 2, 3, 4, 5, 6, 7, 2, 4, 6, 8, 9, right there. So there's our data. It's not exactly on a line, but it's pretty doggone close. So does there appear to be a relationship? Yes. Looks like there's a positive, fairly linear relationship. But we can definitely tell that there's a positive correlation. And that's really all you have to say at this. So looks like there's a positive correlation. So when one increases, the other increases. find the equation of the regression line, the best fit line. Okay, so now we need to go to our formula sheet and get our equations for the regression line. So we're going to have to do an extensions table here. So in our formula sheet here, coefficient of correlation and then regression line, first thing you got to do is complete this extension table. For the coefficient of correlation, you need sum of squares of x, sum of squares of y, and the sum of squares of xy. In this problem, though, we're finding the slope and the y-intercept of the regression line, so we need the sum of squares of xy and the sum of squares of x. So it doesn't look like we need this one. So let's go back here real quick and see what we're going to have to do. So we're going to need the regression line, graph the regression line, interpret the y-intercept, coefficient of correlation. Okay, so we will need all three. So let's start by doing an extensions table here. So let's list x and y, and then we need x squared, y squared, and xy. And I tried to make this problem doable by hand. So x's are 1, 2, 4, and 7. Put a total row down on the bottom. And remember, you can double check these with a calculator. 1, 2, 5, and 9 are our y's. 2, 5, and 9. X squared, we square each one of these numbers, so 1 squared is 1, 2 squared is 4, 4 squared 16, 7 squared 49. Y squared, so 1 squared is 1, 2 squared is 4, 5 squared 25, and 9 squared is 81. And then x times y, multiply these columns. 1 times 1, 1, 2 times 2, 4, 4 times 5, 20, and 7 times 9, 63. And if you add these on the calculator, here you get 14, 17, 70, 111, and 88. Okay, and you should double check these. And in fact, why don't we go ahead and do that real quick. Okay, let's see here. Got to start up a new calculator. Okay, so remember, you want to go to Stat and then Edit and put in your lists. So we've got, for our x's, 1, enter, 2, enter, 4, enter, and 7, enter. Then arrow to the right, 1, enter, 2, enter, 5, enter, 9, enter. So there's our list. And then you go back to Stat, remember, over to Calc, and down to 2 variable stats. Press enter. If you don't get this list, press enter again. And then we can see sum of our x's, 14, right here. Sum of the x squared, 70, right here. We arrow down. Sum of the y's, 17, right here. Sum of the y squareds, 111, right here. And sum of the xy's, 88, right there. Okay, so that's looking good. Okay, so now next what we have to do is we have to find that the sum of squares of x, the sum of squares of y, and the sum of squares of xy. So just go ahead and write all three of those out to start. Again, what I'm doing is I'm writing out here sum of squares of x, sum of squares of y, sum of squares of xy. Because we'll need them here, and then we'll need them down here too. So let's just go ahead and do everything. So this is the sum of the x squared column minus the sum of the x column. That gets squared. and then divide by n. And here n equals 4 because there's 4 points. And let's see. Oh, let's go ahead and label these. So this is the sum of the x column, so that's sigma x. This is the sum of the y's, so sum of y. This is the sum of the x squared column right there, 70. And the sum of the y squared column, 111. And the sum of xy's is 88. So the sum of the x squared, that's 70. Minus sum of x's gets squared, divide by n. So the sum of x's is 14, so 14 squared, and divide by n is 4. So let's go ahead and key that in. Alright, so 70 minus, I'm going to go ahead and use some parentheses. I'll do 14 and see x squared button. Divide by 4, close up our parentheses, so 21. And then down here, do the sum of the y squares minus the sum of y, and that gets squared, and divide by n. So the sum of the y squared column, that's the 111. Minus the sum of the y's is 17, so 17 squared divide by 4. And I'm going to put some parentheses in here because I entered them into the calculator. So let's go back and figure that out. So 111 minus parentheses 17 squared divide by 4, close up my parentheses, 38.75. And then the sum of squares of xy, that's the sum of the xy minus the sum of the x times the sum of the y, divide by n. So the sum of the xy's is 88 minus sum of the x's, sum of the y's, so it's going to be 14 times 17, and that gets divided by 4. And I'd go ahead and put these in parentheses. So let's go ahead and do that. So 88 minus parentheses 14 times 17 divided by 4, close up your parentheses, and 28.5. So we've got all those quantities. So what we need next is the equation of the regression line. So if we go back here, our regression line slope is sum of the square root of the xy over x. Let's write that down. So our m is going to be sum of the squares of xy over the sum of squares of x. And so sum of square root of xy is 28.5. And then we divide by sum of squares of x, 21. And if we divide that out on the calculator and take several decimal places here, there we go, 28.5 divided by 21, 1.35714. 1.35714. Keep several decimal places. And then our equation for b, sum of y minus m sum of x over n. So our b is the sum of the y's minus m times the sum of the x's over n. So the sum of our y's, that's this column here, 17, minus m, that's this guy up here, so 1.35714, times the sum of the x's, that's 14, and then all over n, which is 4. So when you key this in the calculator, either use parentheses for your whole numerator or do the numerator, get an answer, and then divide by 4. So let's see here. So I'm going to do 17 minus, and then parentheses 1.35714 times 14. Close my parentheses. That's my numerator. I'm going to go ahead and get an answer. So negative 1.99996, and then divide by 4, enter. So negative 0.49999. Okay, so now we can go ahead and round here. This is okay, round to 2 decimal places. So it looks like negative 0.5 to 2 decimal places. So this will be approximately 1.36, and this will be approximately negative 0.5. So now our best fit line, remember, is mx plus b. So y hat equals mx plus b. So in our case, that is going to be 1.36x and then minus 0.50. Draw the graph of the regression line on the scatter plot. So start from negative 0.50, and then we want to rise 1.36 and run 1. Okay, so rise 1.36 and run 1. Well, that's a little tough here. We're going to start from negative 0.5, which would be, this is a scale of 1, and this is a scale of 1. So negative 0.5 would be about right here. So if you rise 1.36, you're going to be up to about here and run 1. And then you rise 1.36 and run 1 again. That's a little hard to tell. So what we want to do is we want to do several rises and runs in there to get a better idea. So why don't we take this, our slope here, which is 1.36 over 1, and why don't we multiply the top and bottom by a constant so that we're doing several rises and runs. And it doesn't matter, what you do here. Our last point is at 2, 4, 6, x equals 7. So we could try x equals 7. So if you multiply top and bottom by 7, we could check and see what we get. So 7 times 1.36. 7 times 1.36 is 9.52. So this will be 9.52, and then 1 times 7 is 7. So this is saying if you do rise and run 7 times, you'll go up a total of 9.52 and, 7. You'll run a total of 7. And there's nothing special about 7 except, that's the x-coordinate of the last point right here. So that's why I picked that one. So from this point, you're going to go up 9.52. So this is at negative 0.5. So you go up a half and then 9 more. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you run 7. 1, 2, 3, 4, 5, 6, 7. We are just about right on top of that point. Let me use blue here for our regression line here. So that get that blue point, and then that was at negative 0.5. We rise 9.52. We're going to be like just above this point. It is almost going to overlap that point. It's going to be like right there. Because we rose 9.5 and ran 7. So now our regression line is going to look like this. Wow, those points are really close to that line. Really close. So we should get a coefficient of correlation. Remember, the R value measures how strong the linear correlation is. We should get a really good R value, like really close to 1. Okay, so this part's done. We've got our best fit line and we've got it graphed. So next they say interpret the slope and the y-intercept in the context of the problem. Okay, so M is rise over run. And remember that our rise is y, run is x, and our x here is number of stores, and our y is sales in millions. So the rise is going to be the change in sales, and the x is going to be the change in the stores. Okay? As x changes, you're adding stores. As y changes, your sales are going up in millions. So your rise here, which is going to be 1.36, and that's sales in millions. So this 1.36, which is 1.36 over 1, is $1.36 million, and per one store. Okay, so that slope means that every time you add a store, sales increase 1.36 million. Okay, so that's your interpretation. Add one store, and sales increase 1.36 million. And then the y-intercept, remember the y-intercept is the y-coordinate when x is 0, and ours is negative 0.5. So that's the y-coordinate is the sales, the x-coordinate is stores. So this is the sales when you have 0 stores. Okay, so B, your y-intercept, is going to be your sales with 0 stores. And in our case, that's negative 0.5. So this is saying if you've got 0 stores, you're losing $500,000. And in this sense, it doesn't, in this problem, that doesn't make sense that your sales would be negative, because if you have 0 stores, you're going to have 0 sales. But it would make sense that your profit would be negative, because if you had 0 stores, you could still have business expenses that weren't related to, your stores. So you could have a loss. And then the last thing we need to do is our coefficient of correlation. And then remember, coefficient of correlation is sum of squares xy on the top, square root sum of it squares x, sum of squares y on the bottom. So let's copy that over. So our R value is sum of squares xy on the top, and we're dividing by square root sum of squares x on the bottom, sum of squares of y. Go ahead and plug these numbers in. So on the top, that's a 28.5, and then on the bottom, square root sum of squares of x 21, and for y 38.75. So 21 times 38.75. Okay, let's go ahead and key this into the calculator. Calculator turned off on me here. Okay, so let's see, 28.5 divided by second of x squared gives us our square root, and we want 21 times 38.75, and that is all inside the square root, 0.999. Okay, so that makes sense. So 0.999. And this is really close to 1. So notice that this is approximately equal to 1. And then last up here, what does this R value tell us about the relationship between x and y? So interpret this. Well, remember, when it's really close to 1, then that's a strong linear relationship, and it's positive, so it's going to be a strong positive linear relationship. if I can spell positive here, strong positive linear relationship. And if it was close to -1, then we'd have a strong negative linear relationship. Okay, so that problem's all set. So that's kind of the long one. So, but it should be pretty similar on the exam. This problem should not change much. Okay, now we're up to the probability, chapter 4. So we want to identify our experiment, our sample space, and our event of interest. Okay, so you spin a spinner below 2 times and you hope to get the same color. So, well, your experiment, remember that's what you do to collect information. So the experiment is going to be to spin twice. Spin the spinner twice. And then let's see, we want to identify the sample space. Okay, this is a 2-step experiment. So probably a nice way to do sample space on this one would be an outcome table. So we could list an outcome table here with our first spin on the horizontal and our second spin on the, on the vertical, and our second on the horizontal. So first spin here is going to be red, blue, green, or yellow. So red, blue, green, yellow. And second spin, the same possibilities. Red, blue, green, yellow. And then all possible outcomes could be red on the first, red on the second. So red, red. Red on the first, blue on the second. So red, blue. Red on the first, green on the second. Red, green, etc. Red, yellow. Blue, red. Blue, blue. Blue, green. Blue, yellow. Green, red. Green, blue. Green, green. Green, yellow. And then last row, yellow first and then red. So yellow, red. Yellow, blue. Yellow, green. Yellow, yellow. So this is a list of all our possible outcomes. So identify the experiment, the sample space. Now the sample space is a set. Formally, the set S is the sample space, and it's going to start with red, red, and it's going to go all the way down to yellow, yellow. If you've listed all the outcomes, then I know what this means. Because remember, the sample space is actually a set. And then list the event of interest. Okay, we hope to get the same color. So the same color would be red, red, blue, blue, green, green, yellow, yellow. So that is our event. Well, we've circled the outcomes in our event. The actual event of rolling the same color, let's call that event E. And that event is a set because an event is a subset of the sample space. So that's the set containing the outcomes red, red, blue, blue, yellow, yellow, and green, green. In any order. Order doesn't matter in a set. And then notice that another way to get the set of all possible outcomes here is to do a tree diagram. So you could have done a 4-way tree, 4-way split, red, blue, yellow, green, and then another 4-way split off of each one of those, and that still would have given you the 16 possible outcomes. So there are lots of possibilities for what I could do for an experiment. I mean, I could flip a coin and roll a die, or I could, roll a die and then spin a spinner, or I could spin the spinner and draw a card. But whatever it is, if it's a two-step experiment, you can do an outcome table or a tree diagram. If it's 3 or more steps, then you can do a tree diagram always to get the sample space. All right, now next up we have some card problems here, and you will have a deck of cards available to you. So let's take a look here. We want to find, if we draw a card, so we're drawing one card from a well shuffled deck, find the probability that the card is first a club, and we just want to use desired outcomes out of total outcomes here. So our desired is clubs, our total is going to be the whole deck of cards. So if we go back to our deck of cards here, your clubs are right here. There are 13 of them, and we're not including jokers here. These are just the piles of cards. This is our deck of cards right here. So you got 13 of each suit, 4 suits. So we got 13 clubs and 52 altogether. So 13 out of 52, right there we go. A right off the bat. And notice some of them are reduced and some aren't. So you want to just kind of be careful here. A black card or an ace. So black cards or aces. Okay, so this is, I'm asking, what's the probability that it's a black card or an ace? And that's going to be addition rule. So for black cards, we're going to count black cards, and then we're going to add in the aces and then subtract out the overlap. So black cards, we've got 26 out of 52. And then plus, we've got 4 aces out of 52. So we add the two probabilities. B stands for black, A for ace. So black cards, these 26 out of 52 are black, plus aces, 1, 2, 3, 4 aces. And then what we have to do is subtract out the overlap. So the overlap between the 4 aces and the black cards are these 2 black aces. So those got counted once for the black cards and once for the aces, so we have to subtract them out. This is addition rule that we're using. So minus the double count, 2 out of 52. So that'll be 26 and 4 is 30, minus 2 is 28 out of 52, so D. Notice if you didn't subtract out the double counting, you'd get 30 out of 52, which is B, and that is incorrect. Okay, so make sure that, because this is an OR probability, make sure you use the addition rule and subtract out the double counting. A diamond or a black. Okay, so again, this is addition rule, so we want to know probability that it's a diamond, let's call that event D, or it's black. Okay, well, we do probability diamond plus probability black, subtract out the overlap. So diamonds, there are 13 diamonds, and then black cards, there's 26 black cards. But then notice there's no overlap between the black cards and this row of diamonds. So those are disjoint sets. They're separate from each other. So this is addition rule for disjoint sets. We're going to have our diamonds, which are 13 out of 52. And then we're going to add our black cards, 26 out of 52. And that gives us, there's nothing to subtract out. No double counting on this one. So 39 out of 52. Which is C. Probability it's a black diamond. Okay, let's see here. Well, diamonds are red, so there are no black diamonds. So that's an impossible event. Okay, so there are 0 cards out of the 52 that are black diamonds, so that's B, 0. Probability that it's not an ace. Okay, so that's asking what's the probability that it's not an ace. That's the event A bar, the complement. And remember, that's going to be 1 minus the probability that it is an ace. So that's 1 minus probability it's an ace. There are 1, 2, 3, 4 aces out of 52. So this is 1 minus 4 out of 52. So this is 52 out of 52 minus 4 out of 52 would leave 48 out of 52. D. Okay, so all of these kinds of things you can do, by addition rule, complement rule, and desired outcomes out of total outcomes. Let me do one more example here, just to illustrate one that's got a complement in it and also an or. Well, this one had just a complement, and these had ors. So what if I said, what's a probability that it's not a king or not red? Okay, so this would be, so I'm asking what's the probability in symbols. This is K bar or R bar. Okay, so not king or not red. Okay, well, this is addition rule, so this is going to be the probability that it's not a king plus the probability that it is not red, which means it's black, and then subtract out anything that gets double counted. So minus out the probability that it's not a king and not red. Okay, so first let's do not king. So probability it's not a king. Kings, there's 1, 2, 3, 4 kings. So that leaves 48 left that are not kings. So that's going to be 48 out of 52. Plus the probability it's not red. Well, that's just saying it's black. So there's 26 out of 52. And then we've got to subtract out the double counting. So what are the cards that are not kings and they're not red? So they're not kings, but they're black. So the not kings are these 48 cards here. We also want not red, so it's just the black. So it's these 12 clubs and these 12 spades. So that's 24 that got double counted. So minus 24 out of 52. So that'll be 48, positive 26, and negative 24. This is just 2, so that adds 2 more. That would be 50 out of 52. So there's one more example that give you an idea of how I could change these. There I combined a complement and an or. Okay, the odds of winning a sweepstakes are 1 to 250. What's the probability? So remember, odds are the ratio of successes to failures. So we have 1 success for every 250 failures, so 1 win for 250 losses. Probability is desired out of total. So the probability of a win here is going to be successes out of total. Okay, so that's going to be successes out of success plus failure. So we had 1 win out of 1 win plus 250 losses. So that's 1 out of 251. And then you can go the other way too, remember. If you're given the probability, you can find the odds. So probability is successes out of total, and then odds are success to failure, but to get the number of failures, you just take the total on the bottom and subtract the successes. So you want to make sure that you review how to go the other way on that too. All right, we're getting there. So here we've got a table, and we've divided up drinkers and non-drinkers, and then we categorized how many had various diseases. So we have a total of 95 people, a grand total of 95 people that are included in the data here. 60 of them had cirrhosis, 26 had liver cancer, and 9 had heart attacks, and I labeled those events C, L, and H just to make it easier. Drinkers, we had a total of 82. Non-drinkers, a total of 13, and I labeled them D and N. So from this information, if you select a person at random, what is the probability that the person is a non-drinker? So this is asking, what's the probability of N? So no restrictions here. So this is just desired outcomes out of total outcomes. So this would be the non-drinkers, 13 out of 95. No work to show there. And then you don't have to change it to a decimal. What's the probability a person is a non-drinker and has cirrhosis? So they're a non-drinker, so they're in this row, and they ended up having cirrhosis. So that means this row and this column. And you can see that there were 3 people that were both in that row and that column. So this one is going to be 3 out of total of 95. No given conditions, so no restriction there. And since we had raw data here, we didn't need to use a multiplication rule for the AND probability. Remember, AND probabilities are also overlaps when you've got a probability, when you've got a table here, not quite a probability table. What's the probability the person is a drinker or has liver cancer? So or, that's addition rule. So this is going to be the probability that the person is a drinker, that's D, or has liver cancer, that's L. So addition rule says you take probability of D and you add probability of L, and then you subtract out the overlap between the two events. So that's probability of D and L. Okay, so the drinkers, there were 82 out of 95. So 82 out of 95. Plus those that were diagnosed with liver cancer, total of 26 out of 95. So plus 26 out of 95. So that's this one. And then subtract out what got double counted. Okay, so the 82 that were drinkers here. And then we had the folks diagnosed with liver cancer. We're right here, 26. Okay. And notice that 22 got counted twice, once for the row and once for the column. So we have to subtract that 22 out that got double counted. So subtract out 22 out of 95. So we got an LCD, 82 plus 26 minus 22. And that gives us 86 out of 95. Okay, next up, probability the person has had a heart attack if we know. So that's telling you a given probability. That's conditional. So this is asking what's the probability that the person's had a heart attack. That's the event H. If we know, so given, that they're a drinker. So it's given that they're a drinker. So remember, the given condition restricts the total outcomes. So it's given that they're a drinker, so they're in this first row, so it's out of 82. And then out of the people in this first row, we're only considering that first row, we want to know how many of those people, because it's given they're a drinker, how many of those people had heart attack, which is 3. So you restrict yourself to the first row. So 3 out of 82. No work to show. And you don't have to write these formulas. If it helps you remember what you're doing, that's fine. But you don't have to write this out. As long as I see these numbers here and I see numerator and denominator, that's fine. What's the probability the person is a drinker given that, another conditional, they have liver cancer? So this is asking probability they're a drinker given that they were diagnosed with liver cancer. So that's the event L. So again, the given event restricts your denominator. So we go back up to the table here. And we're restricting ourselves to this column here. So these 26 people. So that's the denominator. 26. And then out of those 26 people here, how many were drinkers? Well, that's the first row, 22. So 22 out of 26. So whatever your condition is down here, that restricts your denominator. And then out of those people, how many satisfy the first condition? So that's conditional probability. Now, I could ask things like, what's the probability the person's a drinker given that they did not have liver cancer? Okay, so that's saying what's the probability the person was a drinker given not L? What would that be? Okay, well, not L, that restricts your denominator, so they're not in this column. So that means they either had cirrhosis or they had heart attack if they're in this study. So that's 60 plus 9 would be your denominator. So we're just restricting ourselves to these people. Now, out of those people, how many were drinkers? 57 plus 3. It's a 7. So this is 60 out of 69. So, and I would want to see these. You wouldn't have to write this formula if you thought it through, but I do need to see these numbers, where these are coming from. So that's just an extra example to give you an idea how I could change things. Are the events H and D independent? So what we need to do is look at what is the probability that person has heart attack, H, what's that equal? And then see if that changes if they're given to be a drinker. What's the probability of H given D? See if those are equal. If they're equal, independent. If they're not equal, dependent. So people that had a heart attack, that was 9 out of 95. And then if it's given that they're a drinker, okay, so it's given that they're in this first row, what is the probability that they had a heart attack? So out of that first row, which is the 82, so your given condition here determines the denominator. So out of 82, how many had a heart attack? 3. Okay, and these guys are definitely not equal. So 9 out of 95 is certainly not equal to 3 out of 82. And if you change them both to decimals, you see they're not equal. So these are dependent. Okay, this probability depends on whether they're drinker or non-drinker. If they're drinker, it's this number. If they're not, it's 9 out of 95. Changes. Are they mutually exclusive? Heart attack and drinker. Okay, well, heart attack is right here. Okay, and then drinker is these people here. And we can see that they are not exclusive. There is overlap. There were 3 people that were drinkers and had a heart attack. So are they mutually exclusive? No. There is an overlap of 3. So an overlap of 3 that had both, or satisfied both conditions. So independent, does the probability of, or does the occurrence of one event affect the probability of the other? Mutually exclusive is asking, do they overlap? Or are they separate? So these guys are not mutually exclusive. And then we're ending up here with some tree diagrams. We've got 6 white marbles and 4 purple marbles in a bowl. If you draw out marbles with replacement, Okay, so with replacement, this is independent. Find the probability they're all purple. Okay, well, let's draw our bin of marbles here. Okay, so we got some marbles in here. Let's see, how many do we have? 6 and 4, so we got 10 total. So I need to close down on that a little bit tighter there. You don't have to draw the picture, just, trying to give you a better idea. Okay, so let's see, 1, 2, 3, 4, 5, 6, 7, 8, and we need 2 more here. We're overflowing. All right, and we have 6 white, 4 purple. All right, so I got 4 purple ones. 1, 2, 3, and 4. And 6 that are white. Okay, find the probability they're all purple. Okay, well, if you take out a marble, whether it's white or purple, you put it back in, then the probability for the next draw, the probability of getting purple is still going to be 4 desired outcomes out of 10 total outcomes. So, so the probability here of getting purple and purple on the first and purple on the second and purple on the third and purple on the fourth is just going to be multiply the probabilities. So the probability of purple on the first times probability of purple on the second times probability of purple on the third times probability of purple on the fourth, which is going to be 4 tenths times 4 tenths times 4 tenths times 4 tenths. So this will be 4 tenths times 4 tenths times 4 tenths times 4 tenths. And then just plug that into your calculator, and it turns out to be 0.0256. So 2.56% chance. And then next we draw out 2 marbles without replacement. Okay, so this is dependent. So we're going to have some conditional probabilities in here. Find the probability the marbles are different colors. Okay, so tree diagram, 2-step experiment. We can draw a white marble or purple. Whoops. Choose P for the event purple. If we draw a white one first and don't replace it, we've still got white marbles left, so we can draw white again or purple. If we draw out a purple one, we've still got purples left, so we can either draw white or purple. And then our outcomes are white on the first and white on the second. So that's white, white, white on the first, purple second, white, purple, purple on the first, white on the second, purple, white, or purple on the first, purple on the second, purple, purple. Say that 3 times fast. And now we want to put probabilities on these branches. So desired outcomes out of total outcomes, chances of drawing a white on the first draw. We've got 6 marbles there that are white out of a total of 10. So this is 6 tenths. And then the purple is 4 purples out of 10, 4 tenths. And then on the second draw, well, if we drew a white one first, then one of these white ones is gone. So now we've got 9 marbles left. So both of these denominators are going to be out of 9. We'd have 5 white ones left and 4 purple ones left. Okay, so both these, right away, both these denominators are going to be out of 9. And if we take one white one out, then we'll have 5 white ones left, but still 4 purple. And then if we drew a purple one first, then one of these guys would be gone. We'd have 3 purple ones left and 6 white ones. So these denominators are still going to be 9 because if we take one marble out, 9 are left. And if we go this way, we took one of the purple ones out, so 3 purple ones are left, but still all 6 of the white. And now multiplication rule, you multiply on the branches. So 6/10 times 5/9, which would be 30 out of 90. And then 6/10 times 4/9. So 24 out of 90. 4/10 times 6/9. 24 out of 90. Or 4/10 times 3/9. 12 out of 90. So there's all our probabilities and all outcomes. And we want to find the probability. They're different colors. 2 ways to have different colors. White and then purple, or purple and then white. Or, okay, so this outcome or this outcome. So we add. So probability of different colors is equal to, that means the probability of getting white purple or purple white, which is going to be 24 out of 90 plus 24 out of 90. So 48 out of 90. And you could reduce this if you wanted to, but it's okay. You could even write it as a decimal if you want to. Okay, and then I think on the other practice exam I did cards for this problem. You know, but it's the same idea. It's still a tree diagram. You've got an event and its complement. You know, here we did marbles. In some of the homework exercises we had, we had other events, but it doesn't matter what your 2 events are. You've got on each branch an event and its opposite. So, one we looked at, flights being on time or late, and that was an example in the notes to see if you could make your connecting flight. So that's another possibility for how I could, change this problem slightly. But they were all tree diagrams, and remember that the sum on your branches has to always be 1, and that you multiply down the branches to get your AND probabilities that are these outcomes here. All right, that should wrap it up for us.